In this episode, we will travel back into the depths of time to relive up close the greatest volcanic eruptions that have raged on the surface of our planet over the past 250 million years. Cataclysmic eruptions with a duration, scale, and violence far beyond anything known in modern times, and you can see on the screen the exact locations where they took place throughout history. Of course, since these eruptions occurred, the world has changed so much that many of their traces have been erased. Yet, even tens of millions of years of erosion have not completely erased them. So much so that the layers of lava spewed out by these colossal eruptions still cover a considerable part of our planet's surface today. Nearly 10% of the Earth's land is made up of strange formations that show us monumental stacks of lava flows stretching as far as the eye can see, which have been called traps. All the red areas you see on the map of our planet are made up of sometimes several kilometers of dried lava. But the strangeness of these landscapes only partially reflects the scale of the type of volcanism that created them. Because once again, I have to insist on this, none of the eruptions we're going to talk about today have any modern equivalent. To try to grasp their full power, we can proceed by contrast. The eruption of Laki, whose landscapes you can see in the image and which devastated southern Iceland for 8 months at the end of the 18th century, is one of the most violent eruptions our planet has experienced in recent millennia. During this eruption, which caused the death of 20% of the Icelandic population and a drop in the average global temperatures for several years, 15 cubic kilometers of lava were spewed out by the volcano. Now, consider that all the eruptions we are going to cover in this episode released hundreds of thousands, sometimes even millions, of cubic kilometers of lava. If their volcanism was so immense, it's because it was of a completely different nature. Because the outpourings of magma that formed these trap landscapes are the result of upwellings. From the great depths of the Earth, mantle plumes rise up with all their power. They weaken the Earth's crust to the point of fracturing it over hundreds of kilometers. At these open wounds, the energy trapped deep within the Earth would find its way through the cracks to the surface, where colossal amounts of magma pour out along the fault networks created by the plume. The extremely fluid lava then bursts into the open air, forming a gigantic network of lava fountains that spread out without really building a volcano, covering areas comparable to entire countries. And these eruptions from another era, which rage intermittently for hundreds of thousands of years, will then cover the fractured surface of the continents and sometimes even the ocean floor with several kilometers of lava. That being said, we will now begin our journey with an eruption that literally tips the scales and will give rise to the Siberian traps. Today, in this region of the world, nearly 2 million square kilometers, an area roughly 3 times the size of France, are covered by several hundred meters of lava. But what appears on the surface is only the visible tip of a structure that was originally 2 to 3 times larger. A large part of it has been eroded away by later deposits and erosion, or has remained trapped deep within the continental crust, where there is a monumental underground volcanic infrastructure. The eruptions that led to the formation of these traps took place at the very end of the Permian. At that time, the Earth was dominated by the supercontinent Pangaea, when a mantle plume rising from the depths of the planet broke through the Earth's crust in the northern hemisphere. For nearly 4 million years in this region of the world, fractures intermittently opened up over hundreds of kilometers, allowing flows of fluid lava to escape and spread out in endless sheets, temporarily transforming the landscape into seas of molten rock before sealing up and then opening again in another weak spot. It is believed intense activity occurred over several 100,000 years. The flow of magma expelled by the open faults could be dozens of times greater than the total amount emitted on average each year by all currently active volcanoes on Earth combined. Then, gradually, the plume that had pierced the continent shifted and weakened, and after 4 million years of volcanic activity, the infernal episode came to an end. When these eruptions ended, 248 million years ago, they left behind an area comparable to the size of Europe, covered by nearly a kilometer-thick layer of lava, as well as a planet drained and suffocated. Because the eruptions on the surface, as well as the deep circulation of lava through sedimentary deposits rich in organic matter, caused the massive release of toxic chemicals and greenhouse gases. The colossal amounts of CO2 and methane injected into the atmosphere caused the global average temperature to rise by several degrees. Meanwhile, dissolved oxygen levels in the ocean are collapsing, and acid rain is leaching and poisoning the soils, resulting in a global-scale biological collapse. In the end, the eruptions that created the Siberian traps not only formed basalt plateaus several kilometers thick in some places, but they are also responsible for the greatest mass extinction in the history of our planet, during which it is estimated that 96% of marine species and 70% of terrestrial species disappeared. Nearly 50 million years later, several thousand kilometers away, another colossal continental volcanic event begins. In less than 1 million years, which is a relatively short time scale compared to the age of the Earth, 5 to 6 million square kilometers of the interior of Pangaea are covered by several hundred meters of lava. The advent of these massive eruptions at the very end of the Triassic, about 201 million years ago, is linked to the rise of a mantle plume that, in the center of the supercontinent, tries to open a new ocean. Subjected to considerable extensional forces imposed by the gigantic volumes of basaltic magma trying to reach the surface, the crust of Pangaea, resisting as best it can, fractures over thousands of kilometers. Along this embryonic rift, some of the incandescent magma manages to make its way to the surface through the opening fissures, releasing ultra-fluid basaltic lava flows that fill in the landscape. Meanwhile, deep underground, the intrusive magma spreading through the crust bake the sediments rich in organic matter and turn the deep rocks into giant distilleries of greenhouse gases. Here too, this intense volcanism will contribute to weakening ecosystems, disrupting the climate and acidifying the oceans, and thus pave the way for a sudden renewal of the biosphere, by wiping out nearly 20% of marine species and a significant portion of the planet's large terrestrial vertebrates. In the end, the continent Pangaea still manages to hold together, and the opening of the ocean fails. But when the volcanism dies down, it still leaves behind a weakened crust, which, several tens of millions of years later, will make it easier for the Atlantic Ocean to form. Over time, the fragments of these vast basaltic plateaus will be scattered by the movement of the tectonic plates. So today, on both sides of the ocean and on the surface of 3 different continents, we find stacked trap landscapes, which are the fragmented remnants of these almost continuous cataclysmic volcanic episodes that nearly broke up Pangaea. Now, let's go back 183 million years to the early Jurassic period to witness the eruptions of Karoo-Ferrar, which began to tear apart the southern part of Pangaea. About 20 million years after the continent managed to resist the attempt to open a new ocean. This region of the globe, called Gondwana, then gradually breaks apart under the effect of the colossal tectonic forces that are battering the continent. And a new magmatic intrusion will take advantage of this new zone of weakness in the Earth's crust to reach the surface. In just 500,000 years, nearly 2.5 million cubic kilometers of lava will be spewed out through 2 gigantic fissures stretching from west to east, over a distance of more than 6,000 kilometers. The arrival of these lava flows, whose rates surpass by several orders of magnitude all current volcanoes, will, in a succession of extreme pulses, smooth out and fill the landscapes over 3 million square kilometers, ultimately covering a large part of what will later become South Africa, Antarctica, as well as a portion of South America, India, and Australia. The eruptions of Karoo-Ferrar will also trigger the torsion extinction, during which, in just about 500,000 years, the gigantic volumes of CO2 and sulfur dioxide released by the eruptions into the atmosphere will drastically disrupt ocean chemistry and cause dissolved oxygen levels in the water to collapse. At the same time, atmospheric carbon dioxide levels will double, going from about 500 parts per million to nearly 1,000 parts per million. On a global scale, ocean temperatures will rise by 3 to 7 degrees. When the Karoo-Ferrar eruptions end and the fractures close up, nearly a quarter of marine species have been wiped out. And the crust of southern Gondwana, weakened by this intense fever, accelerates its fragmentation, relying on the lines of weakness opened up by the volcanism. Yet this crisis, like the ones before it, did not only bring death. It also encouraged the emergence of other forms of life, because where animal or plant lineages disappear, others can take their place. Thus, the ecological niches left vacant by this catastrophe will encourage the diversification of dinosaurs. 48 million years later, at the end of the Lower Cretaceous, the fragmentation of Gondwana is now well underway. And at the site of the rift that is forming between Africa and South America, where the South Atlantic Rift is being born, lava flows begin that will give rise to the Parana and Etendeka traps. In the span of 3 million years, 1.5 million cubic kilometers of lava will spread across the surface over an area twice the size of France. Even today, on both sides of the Atlantic, in southern Brazil and in the northwest of Namibia, we find identical rocks produced during the same volcanic apocalypse. And I won't dwell too much on this outpouring, because the next one is a really big deal, the biggest one we've ever discovered on Earth. And strangely, this one didn't happen above water, but beneath the waves. Today, to the northeast of New Guinea, lies an underwater volcanic monster, the Ontong Java Plateau, which is nothing less than what remains of the largest volcanic eruption by volume to have left traces on the Earth's surface in the last 600 million years. The Ontong Java Plateau emerged in the Western Pacific during the early Cretaceous, 120 million years ago, when an extremely powerful mantle plume passes through the oceanic crust and deposits 40 million cubic kilometers of magma on the sea floor. An absolutely colossal volume, nearly 10 times greater than that released by the already massive eruptions that gave rise to the Siberian traps. To release such a volume of lava, the magmatic outpouring had to emit as much magma as the eruptions of Laki, and do so without interruption for nearly 3 million years. Originally, the Ontong Java Plateau was probably as large as Alaska. And it must have even risen partly above the surface, but the accumulation of lava eventually collapsed under its own weight. Because as layers of magma pile up on the surface, the oceanic crust bends underneath. Today, seismic data tells us that this plateau is made up of 26 kilometers of stacked layers of solidified lava, which is nearly 5 times thicker than the oceanic crust on which the structure rests. It is actually this massive weight that partly allowed this giant stone lying beneath the seas not to be quickly recycled by oceanic plate tectonics, as is usually the case for geological structures formed in the oceans. In fact, the Ontong Java Plateau, which sinks deeply into the moving crust, is difficult to move, and the movement of tectonic plates struggles to make it slide up to the subduction zones, where the oceanic crust sinks beneath that of the continents. Another oddity is that although the formation of the Ontong Java Plateau is associated with the release of 10 times more lava than the eruptions that created the Siberian traps, it is not linked to any major mass extinction. Locally, the sudden arrival of such a large volume of magma in the South Pacific must have deeply disrupted ocean currents and acidified the water to the point of driving many marine species to extinction. But the fact that the eruptions were spread out over time, and especially that the lava did not pass through and burn organic-rich sediments rich in organic matter, and the fact that the gases released by the eruptions were largely absorbed by the waters greatly reduced the impact of this cataclysm, which, it must be acknowledged, was a good thing for the planet. 53 million years after the flows at Ontong Java had stopped, a part of western India, which broke away from Africa and began its long journey north toward Asia, in turn fell victim to colossal magma upwellings. While it was in the middle of the Indian Ocean, almost directly above the current hotspot of Réunion Island. And in just 2 million years, these 1.5 million cubic kilometers of lava are poured out from the future subcontinent. This extraordinary massive volcanism gave rise to the Deccan traps, whose basalt plateaus, several kilometers thick in some places, now cover nearly 500,000 square kilometers of western India. But these already impressive dimensions are misleading because they represent only the part that has survived to the present after 65 million years of erosion. And it is believed that the Deccan lavas initially covered more than 1.5 million square kilometers before time reduced this footprint. The peak of the eruptions that built these stacked lava landscapes occurred within a narrow time window that just precedes and follows the impact of the Chicxulub meteorite, which, at the same time, struck our planet on the other side of the world, bringing an end to the undisputed rulers of the Cretaceous, the dinosaurs, whose reign had already been weakened by the massive volcanic emissions from the Deccan. Then, 65 million years ago, the magma source weakened, and as India continued its journey northward, the hotspot activity persisted, though at a reduced level, giving rise over the following millions of years to the Mascarene Islands, Rodriguez, Mauritius, and Réunion. Barely 5 million years after the lava flows stopped battering India, on the other side of the world, a magma bubble takes advantage of the fragmentation of the supercontinent Eurasia and the gradual opening of the North Atlantic Ocean, which have weakened the crust, to open a fissure system several thousand kilometers long, stretching from southern Greenland to Scotland and northern Scandinavia, and through which torrents, intermittently for nearly 5 million years, forming basalt plateaus hundreds of kilometers long and often several hundred meters thick. Some of these ancient layers are now visible on the surface in certain regions of western Scotland. Here too, as with Ontong Java, the fact that most of the lava flowed onto the ocean floor will lessen the impact of their arrival. The eruptions that form the traps in this region of the world are quite unique, because, unlike most of those associated with the rise of deep mantle plumes, which are relatively brief events that unleash their fury, for only a few million years at most before subsiding, the magma upwellings here never completely stopped. Over the tens of millions of years that followed the peak of activity, large volumes of lava continued to rise, almost always concentrating in the same place, and eventually gave birth to Iceland. In fact, it is believed that the hotspot now located beneath the island, which is one of the most active on the planet, is inherited from a vein opened by the lava upwellings that began nearly 60 million years ago. A vein that never really closed and would have continued to operate at a reduced rate. There is actually another region on our planet today that, after being affected by an upwelling of mantle magma, never truly went dormant. This region is located in the Horn of Africa. There, in the Abyssinian highlands, you find the impressive Ethiopian traps. These solidified lava flows, which in some places accumulate up to 2,500 meters thick, were formed 30 million years ago when Saudi Arabia began to separate from Africa. For 500,000 years, erratic and repeated eruptions drowned the landscapes under 500,000 cubic kilometers of basaltic lava. Each major lava flow phase that built the Ethiopian traps could spew out as much lava as all the currently active volcanoes on Earth do over several millennia. And the location of these flows is no coincidence. They coincide with the beginnings of the opening of the Red Sea and the East African Rift, which created preferred pathways for the magma simmering below to rise up. 30 million years after the formation of the Ethiopian traps, this region remains one of the most tectonically active on the planet, and volcanism continues to slowly write the first lines of a future ocean there. At the level of the Afar Depression, where the African, Somali, and Arabian plates are tearing apart, the thinning continental crust has favored the appearance of classic volcanoes that form and align along the lines of weakness in East Africa. Fortunately for us, magmatic eruptions like the ones we just flew over remain relatively rare on the scale of Earth's history, where they occur only once every 10 to 20 million years on average. The most recent ones, which produced the Columbia Basalt Plateau in the northwest of the United States, began to occur 17 million years ago and ended 6 million years ago. Although the volumes ejected by these eruptions, which left behind a pile of lava covering nearly 200,000 square kilometers of landscape, are nearly 10 times smaller than those of the Deccan, they are still incomparable with any eruptions of the modern era. During the peak activity of the magmatic outpourings that created these landscapes, dozens of times the volume ejected by Laki could come out from a single event at the same time and flood hundreds of kilometers around with lava. Since this system became extinct 6 million years ago, no major lava outpouring has flowed on the Earth's surface. But our planet will inevitably experience more events of this kind in the future. For now, it's impossible to predict exactly where the next large-scale breakout will occur. However, we know that certain regions of the world, à la surface amincie, that are weakened are more at risk than others. If you think you're going to live for millions of years and your goal in life is to avoid ending up directly above a bubble of magma rising from the great depths, then it's better not to invest in real estate in Iceland or in the Horn of Africa, which are among the regions most likely to one day end up buried under lava. Here you'll find a playlist to discover other videos dedicated to the mind-blowing landscapes from our planet's past. And there, an episode dedicated to the regions that were hit by meteorites. And if you have a minute to spare, I'd be curious to know your favorite eruption.